Hi, and welcome to my presentation about predicting long-term collision risk. My name is Jordi Daniels, and it's getting busy. Maritime traffic is still increasing over the last 20 years by 300%. Still, in the whole world in trade, 90% of all cross-continent trade is carried by sea. And this is bringing some implications or some complications in maritime traffic. One thing is, as it's getting busier, more vessels are traveling and also larger vessels are traveling across sea. And while that may not be a problem for oceans and seas, it is a problem in coastal areas and ports. Because as that is increasing, the amount of ships and the size of ships, the size of ports is very difficult to also increase at the same rate. And bring into that mixture as well that more sea structures are being built than ever. Here in the Netherlands, we are building massive windmill parks that even narrow the amount of waterway down more, which brings up the quantity in ships and also the density of waterways, which could lead to more complications and collisions, which is one of the problems that we're countering here. Now, I do not have to tell you about the negative effects of collisions, which are terrible, of course, but also potential collisions, so collisions that never occur at all, have a massive negative side effect, whether that is financial, environmental, by the amount of extra CO2 emitted, or just stress of captains and also other personnel involved. So the problem is quite big, and the amount of casualties is big as well. While still the biggest problem of the biggest casualty cause is still the loss of propulsion power, which accounts for 22% of all casualties. Collisions account for 13%, and two others, contact and grounding, account for 17 and 13% respectively. They add up together to 44%, and they all have the same problem. They all have the same problem, which is navigational nature. So problems with the navigation of ships. And that is something that we would like to counter here. And while the amount of casualties is only 13% for collisions, the amount of fatalities is way higher for collisions. Because when collisions do occur, they are very drastic. And that's why we want to do research on this and try to predict them. But there's another problem, a small problem, which is very heavy impact, which is the data. So AI can work in all sorts of ways. We can use inductive method or deductive method. But there's a problem with the data. The scarcity of data is massive. There's just a lack of observations, because while collisions are terrible and they happen quite frequently, in order to do proper machine or deep learning, there's actually not enough data. But we can move from a different way as well. We can make observations, we can recognize patterns, and then make a lot of assumptions which we guard with expert opinions in order to make hypotheses. And that's what I'm going to present right here, and the theory of how to do long-term collision risk. But why should we even use AI? That's a question I get asked so many times, and the key is in the observations and the pattern recognition. AI is just very strong in this. It can understand billions of rows of data, and don't be alarmed, billion rows of data is what a port produces annually, for example, in our systems. And it can recognize patterns in all those billions of rows of data. So the method of prediction that I'm using is the following process. It's quite a big process. We're moving from predicting the destination to analyzing the route, to predicting the fairway, predicting the speed, calculating ETAs for all positions, correlating paths and ETAs, and then predicting collisions. But I want to highlight just 3 process steps, which are predicting the destination harbor, predicting the fairway, and predicting the speed. And that is what I'm going to talk about now. So first, predicting the destination harbor, which is a classic classification problem. We use the following features for that. And that's actually funny because there's a story attached to this. I was once in Rotterdam talking about collision detection, and an operator triggered me because he said, with just the name of a ship and the way it was sailing through the port, he was able to tell for every ship where that ship was going. And that triggered me into thinking, well, maybe an AI or machine learning application can do this as well. So we actually built that. And we do not use name as of yet because of data regulation items, but it is something that I want to use. We do use MMSI, but we've anonymized that. And from MMSI, we also thought maybe we can use continents, but that does not help that much in prediction. As you can see right here, the feature importance is very, very, very low. So that's it for predicting destinations. We are actually quite good at this right now, but we need more data. That is the key. We need more data. Now, the second step that I would like to explain is how we predict fairways. So when you know where a ship is going, what the destination is, you still need to know how it is going there. And we use quite cool algorithms for that. One is called the evolutionary algorithm, and with a genetic approach, where we actually train a model to evolve over time with all the routes implemented one at a time into the algorithm, which you can see here, moving from stages to stage. On the left, a very, very wild evolutionary algorithm still. In the middle, a bit better with box plots on what routes are normally taken. And on the right, we are actually able to predict the curvature around corners, which is very difficult to do. And this is also a classification or clustering problem that we worked with. Now, the final part that I would like to explain is predicting speed and how we do that, which is a typical regression problem. And it's very, very difficult. Even though it's a very low dimensional problem, which should be relatively easy, speed is hard. It took weeks or months to understand how difficult this actually is. But predictions are getting better. As we input more data and we are able to recognize more of the history of the data, we can get numbers up to 88% accuracy for some routes in where a lot of ships travel. And as you can see by these box plots, with the colors representing the interquartile range, for some routes we are only off 5 seconds when you take the IQR. But this is also heavily influenced by the amount of data. And that is the key in all these 3 process steps. We need more data. But we do have some results, and we're getting quite close. So for example, these 2 ships moving through the Botlek area, we are able to predict 14 minutes in advance where they are, quite accurately, up to some meters difference. And it actually works. So this is not simulated data, it is just real track data simulated to have a collision. And also this track, so 2 ships moving from Nieuwe and Oude Maas, 11 minutes in advance we are able to tell that they are on a collision course using our predictive collision risk models. But it gets a little bit more complicated because we do not, it does not matter whether you take 2 or 3 or 4 tracks. So in this example we take 4 tracks, and you can see in the first image on the top left the 4 tracks are coming together. In the second image you can see the first collision occurring between the first 2 ships from Botlek and Oude Maas. In the third image you can see another collision occurring just before the entrance of Botlek area. And in the fourth image, another collision, which I also highlighted in blue, on the Nieuwe Maas. So it does not matter how many tracks there are, we can predict collisions for them. And this is also the strength of this program. So operators and captains are extremely good in what they do. They are highly skilled people. But AI can help them in situations where they just cannot predict around the corner and help there. And that is also what I would like you to keep in mind. While the captain has this view, the operator has this view, AI has this view. AI can analyze so much data using trained models, up to thousands of rows at the same time, in real time, without any effort at all. And that is the strength of AI. We can take a look at the whole situation, just less in depth, because we have the captain and the operators doing that, and they're extremely good at it. Now for my final slide, I would like to take a quick look at future research, because this is the exciting part. I mean, what are we going to do now? We have these results, and now what? So we are able to process more and more data. I mean, computational power isn't a problem anymore, storage isn't a problem anymore, so we are going to use more data. We are also going to build new environments in order to test our models, to train our models more efficiently, but also to be able to test with with operators and also captains and other key users in order to make sure that our software actually works and our predictions are good and they're viable. Another thing that we want to implement is feedback learning. So are we able to make the models better based off of these expert opinions? And can we implement it then in the models? And then we start confirming the theory. So we're taking the deductive approach. We use the theory and we try to test the hypotheses. But we have to keep some things in mind while doing this. So we can train with more data, we can have new environments, but we should never sit on the operator or captain's chair. And that is one thing that I'm also always keeping in mind. We want them to collaborate. AI and humans can collaborate. They should not be head-to-head together, but they should think together. And while humans are very good in understanding complex situations in a split second, AI is very good in analyzing thousands or millions of rows of data at the same time. Another thing is that we should take a look into or keep in mind management by exception. So my idea is that AI does not take over the job of an operator or captain, at least not in the near future. But AI puts the captain or operator on the case. So we get more of a dynamic like this, where the AI takes all the normal cases, all the things that are predictable, and for everything that is not predictable, that is not normal, we take the operator, we take the captain, and put them on the case, because they are so skilled in understanding something, understanding complex situation in just a split of a second. And then the AI can then present the information in such a way that it increases the situational awareness of the captain or operator. And finally, what we keep in mind is silent VTS, so system-to-system communication, and of course autonomy, which is one of the biggest hypes of this also this symposium, where ships are being built that can sail autonomously. We are also thinking of how should a system-wide approach take a look into this autonomy, and can AI help in that? So that is it. Thank you for listening to my presentation, and if you want to discuss more about the models that we use, or in-depth the data, or anything that we do or that I just showed you, I invite you to come take a look at the Saab booth, where I will be and my colleagues, and we can discuss anything you want. So thank you.